Welcome to module 8 of object oriented analysis and design. In the last module, we had a brief look on the fundamental approaches in object oriented paradigm. Specifically, we talked about the object oriented analysis, that is starting from a requirement and trying to extract maybe at times vague concepts, key abstractions, objects, their generalization into classes. Then to perform object oriented design, that is trying to represent them in terms of the target system on which we would like to realize the system. And we noted that the analysis and design often is an iterative refinement process, where initially you analyze, based on that create a design, and based on that design again you go back and look for further details in the requirements and refine the analysis, have a more refined design, keep on doing this till you reach to a point where you are ready to implement the system or start implementing the system, and you get into object oriented programming, where you use different language vehicles which either supports object based or object oriented programming paradigms to make the expression of the design easy, and in that process you slowly start realizing a system. And once a simple version of the system has been implemented, then you go back again possibly to further analysis, refinement of design, and then refinement of the system that you have already created. So, this is the overall framework. So, now we will go little bit deeper into the aspects of analysis, and we will start working towards characterization and identification of objects, that is key to the whole object oriented paradigm and the concepts of analysis and design here. So, in this module we will start with the understanding of major and essential characteristic elements of object models, and specifically talk about two such elements. The outline as usual will be available on the left hand side of every slide. Now, if we look into object models, then there are four major elements that we need to consider, and our endeavor in this module and the next two would be to understand these different elements of object model. The major elements include abstraction, encapsulation, modularity, and hierarchy. You have heard about these terms somewhat vaguely in the earlier modules. Our objective now would be to concretely define these elements, these parameters of object models, and see how they play out in different examples. In addition to the four major elements which are essential, there are some useful but not exactly essential elements in defining object models. They are known as minor elements, and they include typing, concurrency, and persistence. So, we will start now with major elements, with the abstraction, the core concept of object oriented programming. Abstraction, if we as we have already seen, and we are just reiterating that point, is abstraction is to simplify a problem by omitting unnecessary details. We had seen that human brain is not capable of handling arbitrary amount of semantic complexity. So, things need to be simple at every stage. So, when we talk about abstraction, we first look into what is our intent in creating the description or creating the specification that we are trying to do, and for that intent we look at only certain specific aspects, certain specific view of the system or the subsystem, and ignore the rest of the details. This process is called abstraction, and as we had mentioned earlier, this is also the process of model building. For example, if we are looking into car brakes as from the perspective of a driver who primarily controls a car, all that we are concerned with in the abstraction is pressing the pedal for the brake should control the speed of the car, without much concern in terms of how exactly it happens in the electromechanical or maybe even electronics subsystem that actually controls the speed. So, this is from our Oede book. This is an kind of a cartoonist's view of abstraction. So, there is a cat and two observers on two sides. One certainly looks at the cat from certain gluttonic approaches. The other, who is a veterinary surgeon, looks at, whenever he looks at cat, he gets to see all the internal organs. So, it is the same cat, but the two observers basically look at two different views of the cat as is their interest. To come to concrete examples, let us start with an electrical circuit. Suppose you are asked to design a circuit, it could be any circuit, it could be a staircase lighting circuit, it could be a traffic signaling circuit, it could be more complex digital system circuits and so on. Now, the question is, what should be your approach? An electrical circuit naturally has inputs and has outputs, and they depend on the time. Now, would you like to really go over all possible inputs and their corresponding outputs, and would you like to characterize all possible states that the system can be in? These are in a mathematical sense, these are possible, but in a practical sense these are not realizable. You cannot look at all possible inputs and know all possible outputs. In a different terms, if you knew that, then you actually have a system which can do this and you do not need to design a new system. So, what you will do, you will possibly look at various types of models for the circuit depending on which aspect you are trying to deal with. So, please do not try to understand what these specific circuits are or what their functionalities are, but this is just to illustrate that the different possible models that are typically used for describing electrical circuits. The schematic diagram, the wiring diagram, the timing diagram, the CMOS diagram, the layout diagram, motherboard diagram, and there could be several many more that can happen. So, if we just take a look, when do we use a schematic diagram? When we are interested in primarily analyzing the electrical behavior of the circuit. So, we just want to know how the components are schematically connected without bothering about what kind of wire or what kind of resistor component you are using or what kind of diodes you may be engaging, but you want to use different kinds of electrical analysis models like Kirchhoff's law, Thevenin's theorem, Norton's theorem, superposition and all that, and you engage into a schematic diagram. But when you know that you will have to actually start putting that circuit in terms of a board, and you know that there are possibly couple of hundred wiring connections that could be made, you will look at a wiring diagram which will show how the connections are being made. If you want to see the way the output of a circuit will change with time, typically we will look at timing diagrams. If you are looking into semiconductor circuit, you are trying to realize some kind of a binary logic at a low level, then you will possibly be looking at CMOS gates, the CMOS diagrams. On PCBs, to interconnect components, you will look at layout diagrams. To package components on a physical PCB, you will look at the motherboard diagram and so on. This is not exhaustive, this is just indicative. So, all the point that I am trying to make is an electrical circuit does not have an universal abstraction, it does not have a universal model. Depending on your intent, depending on what you need to do, what purpose you need to achieve, you look at different aspects of the circuit using different models. And when you look at one aspect, when you are looking at the schematic, you are not really concerned about the timing. When you are looking at the timing, you are not concerned about how interconnects happen on the PCB and so on. So, that is what is called the basic objective of abstraction. Let us move to a very different example. Let us say we want to talk about our country India, we want to understand India. You are given that problem, please understand India. What would you do? Would you go to every citizen of India and meet and try to understand what the citizen do? You will visit every house, examine every tree, go to every paddy fields and so on? Impractical, certainly. But what would you possibly do? You will possibly look at multiple different types of abstractions or models which are typically called maps. So, these are just a couple of examples of variety of maps of our country: political, river map, power grid, vegetation, railways, World Heritage Site. If you go to maps of India, you will find that even the list of the different types of maps, different types of models available for India runs into pages. So, if you look into the specific maps, a political map you will refer to when you are trying to study the administrative structure. A river map will tell you about the natural distribution of water resources. The power grid will talk about how the overall power structure is organized and so on and so forth. So, again, when you are looking at a particular aspect, when you are trying to look at possibly you are planning for certain tourism services and you want to make a tour of interesting cultural heritage sites and tradition of India, you will certainly look at World Heritage Site map, ignoring how rivers are connected in India. But you may in the next step need to refer to the railways network map, because you want to abstract in terms of how those tourists will be transported across places. So, depending on your intent, you look into certain aspect and ignore the rest. A third very different example, suppose here we are talking about a hydroponic gardening system. A hydroponic farm is a soilless, sandless, gravelless farm, where you just have a nutrient solution to grow plants, and suppose you are trying to model that kind of a system. Now, what will you need for a hydroponic farm? You will need to control several greenhouse parameters like temperature, humidity, light, the pH, acidity, nutrient concentrations and so on. So, if you are intending to design an automated system, you would need to carry out variety of abstractions or capture variety of abstractions. For example, in this simple case, if I have to control different greenhouse parameters, certainly the first two abstractions are quite obvious. One is I would need to be able to know what these parameters are at any point of time. So, I will need sensors, and since I want to control them, knowing is not enough. If the temperature is too low, I need to increase that. If the temperature is too high, I will need to decrease that. So, I will need actuators. Say for temperature, I will need heaters. I will need several other actuators for other parameters. In a little bit more intangible terms, certainly if we are designing a hydroponic farm, then we will need to have an idea about how plants grow and how their growth plan can be controlled by controlling different nutrients and conditions. So, a little less obvious, but very critical key abstraction in this system would be growing plants, which will decide how plants can be made to grow. So, these are all abstractions, but each abstraction look at a different aspect, and when you look at the sensor, you certainly are ignoring the aspects of growing plant. When you are looking at the growing plant, you are ignoring the aspects of the heater and so on, but certainly you need all these different abstractions to somehow work together for the whole system to be feasible. So, this is the basic concept of abstraction, and we will see that often abstraction is just in isolation, the abstraction is difficult to express. So, what we do is several abstractions of the same problem are often possible, and we are focusing on some, ignoring the rest. For each abstraction, we have a different model. We have just seen several examples of this. Now, when the problem actually is complex, which is the typical target systems that we are looking for, then a single level of abstraction is inadequate. This is a key point that you will have to remember, that if you want that, you will take the whole system and you will create a set of key abstractions for the whole system, you will often find that it is extremely complex. So, what you do is you resort to the concept of hierarchical abstraction, that is, you try to model a layer in abstraction and you model that using the abstractions of the lower layer, combining the abstractions of the lower layer. Then the layer that you have actually modeled will be used, will be implemented in terms of the higher layer of abstraction. In this process, you create a hierarchy of abstractions for the whole system. Let us look at examples. Say we look at you are given to study the life forms that inhabit earth. Now, naturally it is impossible to look at every living organism. So, what will you do? You will do a hierarchy of abstraction. So, if you look into this hierarchy, these are more towards below at the more specific species. The hierarchy could go even deeper, even within the species we could have, for example, Homo sapiens is us, Homo sapiens is human beings. So, we could have hierarchies go deeper than that, where you can say that there are ethnic groups amongst Homo sapiens and so on. But if we just start the species to be the starting point, then there are several of them. So, instead of looking at those abstractions directly, you group them in terms of their commonality and have multiple layers in this. When you come to phylums, you aggregate phylums together, you combine them together in terms of their commonality and come to the basic kingdom of living organisms, where you talk about Animalia, Plantia and fungi, which say that the basic living organisms are either plants or animals or fungus. And there are certain common properties certainly which decide this hierarchy at every stage, and from the problem requirements, from the problem specification, it is our job to be able to extract this commonality and organize this hierarchy. But the basic requirement of a hierarchy is very critical, because that helps us to manage the complexity of the abstraction in a much better manner. Let us look at a little simpler problem, but even I am referring back to the leave management system, of which you are already aware, and you know that in this we can have abstractions of employees, executives, there are lead engineers, there are managers, and we can express that in terms of a hierarchy here. So, what we are saying is an executive is an employee, a lead is an employee, a manager is an employee. So, in that process, if you just look at the specific characteristics, then the employee, which is more generic in terms of abstraction, has a few characteristics, and therefore, all the specific executives, lead and manager will also share that characteristics, but they could have additional characteristics. For example, an executive will have a characteristic that he or she has a reporting lead. Similarly, a lead will have additional characteristics to say that a lead has a reporting manager, and in turn has a list of executives who report to this lead. Manager has similarly additional characteristics. In terms of the behavior of or the responsibilities that this abstraction carry, few are common at the level of employees, which mean that all specializations, all lower level abstractions will share those responsibilities, but there could be few additional responsibilities which are specific to the lower level abstractions, like executives will report to lead, lead can do so many other things, managers can do so many additional responsibilities and so on. And in this process, this is again this is not unique. We could for example, we could create a different kind of hierarchy, saying that this is my employees and this is my executive, this is my approving employees, this is my lead, this is my manager. I could create a hierarchy of of this kind also. So, what I do is necessarily I introduce a new abstraction saying approving employee, because I observe that between the manager, if I take approve leave, regret leave, revoke leave, tape reporting, these responsibilities, I find a commonality between the lead and the manager, and therefore, I can think of that I have another abstract concept, all those employees who can approve leave for someone else. Executives do not fall in that category, because they cannot approve leave for others. So, they separate out, but here I have another abstraction of approving employees who specialize into the next level of hierarchy in terms of either leads or manager. So, my whole point of illustrating this is to emphasize that abstractions are better expressed when put in hierarchical terms, and those hierarchies are not unique. If you look back into the hydroponic gardening system, we have talked about sensors, so we can easily see a multi-level hierarchy that happens in that you have sensors, which generally will have a characteristics of you need to know where the sensor is, and every sensor will need a calibration. So, that is a basic property of a sensor. Then I have a temperature sensor. So, in addition to location, its characteristic is temperature and to be able to report the current temperature. Then I may have an active temperature sensor, which is kind of not just sensitive at certain points of time, it is available every time. It can set a point to function and so on. So, it has more characteristics, more behavior, and therefore, this is what forms a hierarchy which can also be multi-level in terms of the abstractions. The next concept or the next major element that object models will need is known as encapsulation. Encapsulation means to encapsulate, that is, in very simple terms, like all of us are more familiar with the term capsule, and we associate it with drugs, medicine, right. We always, if we fall sick, then we either have tablets or we have capsules. What is a capsule? Capsule has, if you just recall, I am sure all of us have had the unfortunate situation of having to consume capsules. You will find the capsule has a coating which does not basically taste, but if you have ever ventured into opening a capsule and trying to taste the actual medicine inside, it will be usually a very irritating taste. So, the purpose of the capsule, which has given it the name of the form of administering the drug, is to shield, is to encapsulate the bitterness or the irritability of the medicine from the acceptability of the tongue, and encapsulate is basically that concept applied in terms of object oriented system. So, it says that you put everything in terms of I would like to change the color of this pen. Let me go to red. This is now red. Okay. So, put everything into an envelope. Why do we, when we put 5 pages of a letter into an envelope and seal and post it for delivery to the recipient, we are also doing encapsulation. So, we are basically putting many different things together, so that they stay together, and to provide others to use it through a well defined, well planned orifice. So, how you use the content of an encapsulated entity has a well defined plan. So, if it is a medical capsule, that plan is to be able to swallow and take it to your stomach, where the acid will dissolve the capsule coating shield and make the medicine work for you. If it is a envelope, then your idea is to retain it for the purpose of expressing the sender and the recipient, more importantly the recipient address, so that it can reach at the right point, where the envelope can be torn apart to find the content, letters and so on. So, there are two things in the encapsulation. So, I am just talking about physical examples. In conceptual terms, there are two things that you will need to deal with. One is putting things together as one entity, and the other is mechanisms to be able to provide access to the contents, maybe at times selective basis to with according to a specific plan. So, encapsulation compartmentalizes the elements of an abstraction that constitute the structure and the behavior, which means that we have known that abstraction has a structure, abstraction has characteristics, and it has responsibilities, that is the behavior. So, we could encapsulate both of them in different separate forms and make them to work together or separately as needed. So, this is a cartoon again. I just love these images from the book. So, it is as if the whole skin and the outer muscular layer of a cat encapsulates what is there inside. This is a more concrete example of opening up a personal computer, and if you open up, I am sure all of us have had experience of looking into that. You find that there is an outer cover, which is the outer encapsulation, and which exposes only a few of the inner usabilities. Like you will need to have a power input point, you will have few USB ports, you will possibly have a serial connector, you will have some LEDs showing you the if the machine is on or if it is off and so on. But other than that, it is all encapsulated in terms of this kind of a big big carriage. But if you open inside, you will find it is not that thousands and millions of transistors or ICs roam around. You will find other encapsulations here, could be the power supply, it could be the motherboard, it could be the drive, which themselves are encapsulated, and if you want to take them out, you will be able to do that, and in each one you will again find that there is a orifice of use. If you take out a power supply, you will find there is a power in which takes in the raw power, and there are certain power out points which give you different kinds of stabilized DC voltages, maybe plus minus 5 volt, 12 volts and so on. So, if you look take out a drive, say the hard drive, you will find that the hard drive has power input points, hard drive has address and data bus connections that need to be done, but rest of it is all encapsulated inside a physical cabinet. Now, if you happen to maybe lot of unused old systems lie around, so you may want to open up a hard drive and see what is inside, and you will find that there are certain boards, components, PCBs on that, and there is actually another encapsulation of a physical drive that exists inside, which again if you open up you will find different actual disk platters or whatever different things that exist. So, the idea is to show that encapsulation is a basic process by which you put things together and give very selective usability, selective access to different people who need to use that. And coming straight to computer science, encapsulation is something you can understand in terms of if you are trying to create a stack, it has to have a structure and behavior. The structure must contain two things: a container to keep the values that I want to stack, and a marker to mark the top of the stack. And there could be several different ways in which I could actually keep the store in terms of array, list, double ended queue and so on, and accordingly there could be different types of markers, and that is what I illustrate here. I am suitably using a little bit of notation which you will over time get adjusted to. I am using little bit of UML here to write and to demarcate that this minus symbol between in front of store and marker basically show that these are guarded part of the structure. These are heavily encapsulated and cannot be taken out at all almost. And then I have a behavior which basically tell me that these 4 behavior are what designates a stack. So, this part is encapsulated and this is the orifice through which you use a stack. You really do not, You may have a stack which is on array, on a or on a list or on a deck, you just really do not care as long as your orifice is the same, your use model is the same. So, that is a basic property of encapsulation. It hides the certain interesting parts of the implementation from the contractual interface.